Now I want to explain entropy, cross-entropy, and the KL divergence, and how they are used in machine learning.
First, I want to define surprisal. It measures the level of surprise that a random variable x takes a specific value. If this value has a low probability, we do not expect that to happen, so when it does happen, it will be very surprising. Low probability means higher surprisal, higher probability means lower surprisal. Mathematically, surprisal is defined as the negative log probability, or shown in this curve. Given a log base of 2, the surprisal is measured in terms of the number of bits.
The expectation of the surprisal is the entropy. It describes the overall uncertainty in a probability distribution. For a random variable x, entropy measures the mean surprisal of x, while x is drawn from its probability distribution px. By definition, this expectation is the average of surprisal weighted by the density over all possible values that x may take. Let's look at some examples. Here shows three Gaussian distributions. The blue and the green distributions have different means, but the same variance. Their entropies are identical. For comparison, the orange distribution has the same mean as the blue distribution, but has a smaller variance and a lower entropy. So, in general, for a Gaussian distribution, the entropy depends on the variance, not the mean. Higher variance means higher entropy. Here is another example for a discrete binary variable x. It means two possible outcomes, x being 0 or 1. If x equals 0 versus 1 has about the same probability, then knowing this probability does not improve our ability to expect whether x will be 0 or 1. Any guess we make will be up to a chance level. In this case, the entropy is high. If we know that the probability that x equals 0 is 0.1 and the probability that x equals 1 is 0.9, then we are much more certain about our expectation, which is x is likely to be 1 rather than 0. In this case, the entropy is lower. We can generalize the formula of entropy to any data distribution. But for real-world data, the data density, piece of data, is unknown. So we cannot really measure entropy or have a closed-form solution for entropy. Using machine learning, we try to model the data distribution P sub data using a model distribution P sub theta, where theta is the learnable parameter. Given any sample x drawn from the unknown data distribution, we can measure its probability and the surprisal under the model distribution. The expectation of the surprisal under the model distribution is the cross-entropy between P sub data and P sub theta. So cross-entropy is always between two probability distributions. The first distribution is where we draw samples. The second distribution is where we evaluate the probability and the surprisal. In this context, the first distribution is the unknown data distribution. The second distribution is the model distribution. If we use P sub data for both the first and the second distribution, then the cross-entropy between data distribution and itself is simply the same as entropy. We should note that the cross-entropy is asymmetric. So if we switch the first and the second distribution, the cross-entropy will simply be different.
From this perspective, we can compare cross-entropy and entropy side by side. Their difference is under which distribution we evaluate the surprisal given samples from piece of data. We may think about this difference more intuitively. While the model P sub theta approximates the data distribution P sub data, the model cannot be more accurate or informative about data than the data distribution itself. That means the same samples will be more surprising under the model distribution than they are under the true data distribution. So cross-entropy is always greater than entropy. The difference between cross-entropy and entropy is known as the KL divergence. The KL divergence is a measure of the distance between two distributions. In this case, it is the distance between the true data distribution P sub data and its model P sub theta. We can derive and write the KL divergence in three equivalent ways. To recap, the KL divergence is the difference between cross-entropy and entropy. While the model density perfectly matches the data density, the KL divergence is zero. In general, the KL divergence is greater than zero or equal to zero. Recall that we can use maximum likelihood estimation, or MLE, to learn the model P sub theta that approximate the unknown data distribution P sub data. This is the loss function for MLE. A learning algorithm would optimize theta to minimize the expectation of negative log likelihood under the model distribution for samples drawn from P sub data. We can now see that this loss function is exactly the cross entropy of P sub data and P sub theta. We can write the cross entropy as the sum of the KL divergence and the entropy. Because the entropy does not depend on the learnable parameter theta, so we can ignore it. Now we can see that the maximum likelihood estimation is essentially equivalent to minimization of the KL divergence between data and the model distributions.